State the multiplicity of the zeros. So starting with, like, what do you do first to find a zero? Let's start with that. How do you find a zero? Maya. Yeah, set it equal to 0. And then you need to find the variable, in this case t. So Maya, what would you do to find t? Yeah, take out a t if there's a GCF, take it out. And then try and factor it a little further. How does it factor?
T and then t minus 2.
Right. Because this is a trinomial perfect square. The two numbers that multiply to be 4, but combine to be a negative 4, or negative 2 and negative 2. If you had it written as t minus 2 and t minus 2, that's okay. But when those factors are the same, we combine them together and make that one quantity square. So the zeros would be t equals 0 and t equals 2. But what would you also place with that t equals 2? It has a multiplicity of 2, and we call that a double root. So a multiplicity of that, what do you think a multiplicity means?
Like you get the answer 2 twice.
Yeah, you get the answer multiple times. So a multiplicity is just how many of the same zeros exist, or how many times does it exist. So you get the 2 twice, which means it has a multiplicity of 2, or we call it a double root. It's occurring twice. The 0 would be a multiplicity of 1, because it just occurs once, and it's a single root. Graphically, that means something. So we'll look to see today, like, how does that correlate with the graph when you have a single root, or a multiplicity of 1, versus a double root, or a multiplicity of 2. It really does mean something about the graph as well. Any questions with that? Any questions with your homework?
I did not do that. I did number 59. Did I do it right?
Oh, you did. You were like just skipping 55 and doing 59.
I have 55 up there. I don't know why I did 59.
Oh yeah, that was finding the yes. Just getting those values because they weren't. That one wasn't factorable. Yeah. All right. So then, in your packet, looking at page 18. Yesterday we did part A of both of them, which was finding the zeros. Our goal today will be to determine the end behavior and try and graph as much of the function that we can without relying on a calculator. And I'd actually just like to say, forget about the max and min, and try and graph everything that you can and just like estimate where you think the max and min would be. But we should probably practice finding max and min as well. Like, to me, the more important thing is, can you analyze a graph without the aid of a calculator? Because calculator gives you the answer. Like, after you see the picture in the calculator, you're like, oh, that's what the graph looks like. But I want you to be able to graph it, like, mentally thinking, what does this mean? How does it relate to the graph? What does this mean? How does that relate to the graph? Which is why I don't like calculators. But you have them. So if you look at the first one, just kind of reviewing what we did yesterday. So we found the zeros. The top number, the top power tells me how many I can have, so I can have 4. Once we factored it, we noticed that there were 2 zeros, multiplicity of 2 or a double root. And then we had a 0 at 5 and a negative 4. So part B says determine the graph's end behavior, which was really the other thing we looked at yesterday. What part of the function determines the end behavior? So x to the 4th minus x cubed minus 20x squared. There's 3 different terms there. Which part of that, which one of those terms determines the end behavior, Maya? The first one. And it doesn't necessarily have to be the first one, but it's the largest one. So the largest power determines the end behavior and the coefficient in front of it. So since this is even, the power is even, and there's a positive coefficient in front, Maya, what would the end behavior be?
As x approaches negative infinity, y approaches positive infinity, and as x approaches positive infinity, y approaches 1.
Right. So remember, x approaching negative infinity means on the left side of the graph, it's going up. That would be the easy way to say it, the non-algebraical way. And then on the right side of the graph means as x goes to positive infinity, y is still going up. Because even functions do the same thing. They either both go up or they both go down. And since it's a positive even function, both my pieces, left and right, should go up. So now we're not going to use the calculator. We're going to try and make a sketch of the graph from the intercepts and the end behavior. So if you look at your graph, mine is really light. I don't know how yours appeared, but mine appeared really light. Plus I tried to be cute and have this little jack-o'-lantern pattern behind it. So I'm going to place a couple tick marks on here just so that we can see a little easier the graph. So 3 points I'm plotting on the x-axis because that's where a 0 is. A 0 is when y is equal to 0. So on the x-axis I have the 3 values. 1 at negative 4, 1 at positive 5, and the middle one at 0. So plot those 3 points. Then use the end behavior. So Maya just told me as the x goes to negative infinity, which means on the left side of the graph, my y is going to positive infinity, or the left side of the graph is going up. So I'm going to go to my left intercept and literally make it go up, because that's where the end behavior is going. It's going up. It's going to positive infinity. I'm going to go to the right side of the graph, which is the positive 5. Again, the right side of the graph also goes up, so I'm going to make that side go up as well. So by using my 3 points in end behavior, I now have the left and the right side of the graph complete. But we need to finish the middle as well. And this is where the multiplicity kind of creates the graph. So we said that the 5 and the negative 4 are single roots. When you have a single root or a multiplicity of 1, your graph at that point crosses through the x-axis. So when the multiplicity is 1, it goes through your x-intercept. That happens twice, at negative 4 and at 5. So if it's a single root, if it occurs once, it goes through it. What do you think happens at the double root? Odette?
It goes up to the x-axis and goes down again.
Yeah, so it actually goes up to it on the one side, but it's a double root, so on the other side, it's also touching. So a single root crosses through the double root, it goes up to it and then curves and continues in the other direction. That makes this part here a max. So a double root will create a max or a min in the graph. So I know immediately that this is a max at 0, 0, because it's not going to go above that, because if it did, then it wouldn't be a double root, because then it would cross through. So the shape of this graph looks kind of like a W. And we can do that without using a calculator, by using end behavior, zeros, and then the multiplicity of the zeros. However, we do need to try and get the max and the min. So if you go to your calculator, we're going to see if we can figure out how far down these go. And unfortunately, you can't do it yet without a calculator. And you won't be able to do it until sometime next year. So, sad, sad. If you plug the equation in your calculator, you should see a similar graph. So here's where, like, once you have the calculator gives you the answer. And I can't really tell if you're actually thinking about how it graphs because you got the calculator just to find it. Except, can you see the bottom of the graph in the calculator? No. So Kevin, what do you think you'd have to do so that I can figure out where the bottom of the graph goes? We could zoom out, but sometimes zooming out zooms everything out. Kevin, what would the other option be? Go to your table, or how about let's go to the window? There you go. That's great. What one thing could we change in the window, Maggie? Yeah, the y minimum. So zooming out changes everything, which is fine. But if we just use the minimum value and change that, because that's the only part of the graph we can't see. We just can't see the lower part. You have to do a little bit of trial and error. Pick a number, plug it in. It has to be negative, below negative 10. If it doesn't work, pick another number and try it. So I'm going to try negative 50. I'm going to graph it. And then just kind of look. All right, well, definitely is getting better because these are getting closer together. But I still can't see the bottom. So go back to window. Try it a second time and pick another number. Sounds like some are getting pretty close, but not quite. Anybody get a number that works? Negative 200. Odette, what'd you get?
Negative 140.
Negative 140. Either one is fine. Doesn't matter. We can use negative 140, negative 150. I think I had 150, but 200 works too. As long as you can see the bottom of the graph. So now I can see the very bottom of the graph. So the bottom of this right side must be really close to negative 140 because I can just see the bottom of the graph. Odette, how do you get the minimum values then? Both of those are min. So
Go to second trace.
yeah. So now that we have the graph, go to second trace. Number 3 is minimum. And remember that little blinking cursor needs to be close to the minimum value, and you have to do it twice. So you need to be on the left side of the lowest point, and it's the lowest point in respect to the points around it. So there are 2 minimums because there are 2 low values with respect to the values around it. We try and round to 2 decimal places unless otherwise noted. So negative 2.81 and negative 73.39. That would be 1 minimum. If you haven't done so, see if you can find the other minimum, and then we'll talk about how to finish this graph, kind of wrapping it up using those minimum values. What's the other minimum value? Dylan, what do you have?
3.56 and negative 137.97.
So that number was definitely pretty close to negative 140. So when we graph this, obviously our graph doesn't go down to negative 137 or even negative 5 because it probably only goes down to negative 10. We are going to continue the graph, but we're going to continue it with little dashes. And that kind of shows the person looking at it that it's too big to fit on your graph, and it doesn't necessarily correlate with the information you have. If you label that point right next to it, that lets the person know that, yeah, the point does go all the way down, but we can't fit it on our graph. The other one better not go down as far, so it still should look similar to what you see in your calculator screen. So make sure that the one on the left doesn't go down as far as the one on the right. And that minimum is negative 2.81 and negative 73.39. My x value should be pretty close, but the y value we can't go down. Questions? So if you look right next to letter B, make sure you have the max because it did ask us for both. The max is that point right there. That was our double root. So the max was the double root. The min would be the 2 values we defined in the calculator. So looking at the next one, we already found the intercepts, the zeros. The end behavior, even and a negative in front. So it's even and negative. The other one was even and positive. So my graph should do the opposite now. Since it's negative, it should go down instead of it going up. So my y goes down on the left, and on the right. Then plot your points. So we have a -1 and a +1. And then we have a value at 0. And then really try to think about graphing that without just relating to that calculator, relying on the calculator's powers. So the end behavior, the left goes down, and the right goes down. So go to the left point, the right point, make them go down. The values that are single roots are the -1 and the +1, so it should go through them. So it cuts through the single roots. It touches the double root both from the left and the right, so it'll make a curve there. This time, when it's touching it, it's a minimum because it's going down this time, where the other was a maximum because our graph was going up. So we need to kind of figure out what the maximum values are of this graph, and again, that's where you're going to have to rely on the calculator. But I think you could probably graph it without relying on that if I wasn't so worried about what those max values were. So find the two max values. The min is the double root at 0, 0. So Jacob, what did you get for the max on the left?
On the left, -0.71, 0.5.
And on the right?
+0.71, 0.5.
Would this graph be symmetrical?
Yes, sir.
How do you know?
Because both max are the same.
Yeah, both max values, you have a negative and a positive. X values are opposites, so that's y-axis symmetry. Same with the x, two x-intercepts, a negative and a positive value. So this would have y-axis symmetry. Questions? Don't you wish you didn't have a calculator so you could just all think about this and not really worry about the calculator? I'll convince you by the end of the year you don't need it. That'll be my goal. At least 75% of you. My goal is that you don't need to calculate it. 75%. We'll shoot high. 25? 75. 75 of you by the 75% by the end of the year will say, no, I don't need that calculator. All right, two other problems that we're going to look at today. The problem at the top of the next page gives you the zeros. So we just had a 0 at 0, 1 and -1 for the last problem. Here are zeros at 0, 2, and 5. It says multiply the polynomial out, find the polynomial that has these zeros. How would you find a polynomial that has these specific zeros? What do you think you do to get a polynomial? How would you find a polynomial? Jacob, what do you think?
So they're factors.
Yeah.
Yeah.
So a 0
Just need something.
can be a factor. Those are equivalent statements. It could also be an intercept if we were writing it as an intercept, but we can write them as factors. So something that is a 0 means that it can also create a factor. So if it was a 0, I would know that x is equal to those three numbers. So then, Jacob, if I write them as a factor, how would you write them as a factor?
That would be x, and in parentheses, x minus 2, x minus 5.
Could you make this first x anything that you wanted to? Like an x squared, an x cubed, an x to the fourth? Technically you could, because it doesn't specify that 0. So if I said it was a double root, then you'd put a 2 with the x squared. If it was a triple root, then you put a 3. But like technically that 0 there, it could be a double root, it could be a triple root, it could be a quadruple root, but we'll just keep it as a single x. And then how do you multiply it out, Jacob?
Foil.
Yeah, you FOIL it. Usually we FOIL the binomials together first and then just distribute that term through. So Jacob, if you FOIL it, you get
X squared minus 7x plus 10.
yeah. And then distributing the x, making sure you're rating it as a function because it is a polynomial. This is a polynomial in standard form. We usually factor it to get the zeros, getting it in factored form. That kind of worked backwards through the problem. So we factor it to find the zeros, or I could FOIL it to get back to the original polynomial. That's why they're my two favorite F words. Factor to FOIL, you FOIL to factor. It's wonderful. Friends are good too. Yeah. That is also good. Yeah. All right, the last problem we're going to look at today. You should factor with friends and family. There you go. The last one says sketch the polynomial, like we did with the last two, by finding all intercepts, the maximums, the minimums, and the end behavior. How many zeros would this polynomial have? 5. So the power is t to the 5th, so we're going to have 5 of them. Again, we're going to save the maximum for the end, so let's work on the zeros first by setting it equal to 0. They all have a t in common, so we'll pull out that t. It's okay that it says t to the 4th. It doesn't mean you can't factor it. It's still a trinomial. So a trinomial is that AC method. Quinn, if you have a 9, what two numbers multiply to be 9, but combine to be -6? -3. Quinn, what do you put in front of those factors since it's t to the 4th? Yeah, it's t squared. How else could I write that?
0 equals t, and then parentheses t squared minus 3 squared.
Right, t squared minus 3,
Squared.
quantity squared. So the factors are the same. Again, this was a perfect square, trinomial. So now we're trying to find the intercepts. So I know one of them is at 0. So I could write that as 0, 0, since it says intercept. The others are from this quantity right here. So if I solve that, taking the 3 to the other side, it's t squared. So we have to take the square root. Oh. What happens when you take the square root to solve for something that's squared? Plus or minus. So that means my other intercepts are at the square root of 3, 0. What's special about that square root of 3, Connor? It is a double root. Why is it a double root?
Because the quantity t squared minus 3 squared.
Yeah, that quantity was squared. There were 2 of those quantities. That means the positive square root of 3 is a double root, and the negative square root of 3 is also a double root. That's how I get 5 answers. 2 of them with the positive root 3, 2 of them with the negative root 3, and then 1 at the 0. So now I have 5. End behavior. So my largest power is a t to the 5th, and it's positive. So odd and positive. Think about what the graph should look like if it's odd and positive. Kevin, what does the y do on the left side? Goes down. And on the right side? Goes up. Okay, so we have the intercepts. We have the end behavior. We're going to try and make a graph. Without using your calculator and using that wonderful brain. The square root of 3 is really close to the square root of 4. And the square root of 4 is 2, so the square root of 3 has to be a little less than it, right? And you have these little tick marks. So, I mean, you're putting a point close to 2. You don't need a calculator for that. The end behavior. Kevin said the left goes down and the right goes up. And then what happens at a double root? It touches it and curves the other way. So here's it touching, curving the other way. Touching, curving the other way. At the 0 value, that was a single root. So it has to just pass through that. So these curves are going to go up so high, and then we're going to pass through and somehow connect. How high do they go? That's where you got to use the Crummy calculator. No darn.
Dang it, calculator.
So the last thing that we would have to do would be to get this top max here and this bottom min here. The other max and min are already on our graph. So the max here is negative square root of 3, and this is positive square root of 3. I think they're like 4 something. It's like 0.78 and 4. Am I right? 0.78? Anyone look? Allie.
So if it's odd positive or whatever it is, it doesn't always kind of follow a similar pattern.
Yes.
Okay.
Yes. Odd and positive always follows a similar pattern. Odd and negative would be the opposite. Other questions? Please make sure you're paying attention to the directions on the assignment sheet. Tomorrow we're going to wrap this section up. We have to talk about the intermediate value theorem. And then you'll have some time in class to practice. 71, or let's start with 41 and 71. Volunteer for 41 or 71.
I did my
Emma? 41? Kevin?
Kevin's already done.
Oh, Kevin's already done them. Kevin, who do you want to pick? Who are you going to pick? 71. You got it? Thank you, Dylan.
I have to write it on a separate page.
That would be awesome.
You raise your hand every single time, every single question on the